I did some work on this, and I uploaded it, and I did some more work and I hadn't uploaded it, the most recent, which was just this morning. And I realized I'm kind of beating a dead horse with some of the stuff, so I'll upload that, but and I'll try to not beat a dead horse in class. But hopefully by now you're starting to understand how it is that kVp is so hard to understand, because there's a lot of moving parts to it. So we're going to get into some of the other claims, and we're going to have to back up a little bit and look at some things that we've already looked at to gain context for what we're going to talk about today. So let's get out of this real quick. So we spent the entire time last time talking about the first claim, and that is kVp has more effect than any other factor, and that was true because it changes the REM spectrum, it changes the imaging characteristics of the X-ray beam, which we're going to take a look at today, if not on Friday. We're going to take a look at how it behaves in different tissue types. So it changes the imaging characteristic of the beam. The higher the kVp, the more penetration you're going to get through all different types of tissue. Changes differential absorption, changes the quantity and quality of the X-rays that we create, and it has an exponential effect. There's a direct effect in that if you increase kVp, you get an increase in penetration and an increase in the number of photons at the image receptor, but it's exponential, right? So a 15% change equals 100% change in the amount that you get at the image receptor. So that's where we were on Friday, right? Today being Wednesday, we're going to talk about several of the other claims. I don't know that we'll get all the way through it. We're at slide 33 and it goes through 70. So some of those we're going to go through pretty quickly and some not so much. So claim 2, increase in kVp increases patient dose. All right, so that is absolutely true in the diagnostic range, and that is because as we increase our kVp, we increase the quantity of photons that we create. Since the increase in kVp increases the output, that is quantity, and we tend to think quantity is mass, and it is, but mass is only quantity. So kVp is quantity plus quality plus penetration, plus, it's just all those other things. So we reserve quantity specifically for intensity, and intensity is mass. So in any question that you ask, unless it specifically references kVp, if the question asks, what do you use to control quantity or intensity, your answer is not kVp, it's mass, right? So then if it asks, what is the effect of kVp on quantity, your effect would be, it's direct and exponential, right? So 15% increase in kVp, is equivalent to double the mass, and we're going to get there. Double the mass at the image receptor. If you decrease your kVp, it cuts it in half. All right, so since kVp increases the output from the X-ray tube, then patient dose is going to go up. So we're just going to keep the math simple here, and we're going to look at really kind of the statistics here in a bit. But just to keep it simple, we're going to say that if you increase your kVp by 15%, the patient dose goes up by 30%. It doesn't, but we're just going to say that just to make it simple. So 15% change in kVp equals a doubling of mass, and that's true, but it's in context, right? So we already looked at how much of a change in kVp we get, or how much of a change in quantity we get as we increase kVp, and at the tube output, that only changed by how much? Remember?
70.
Roughly 70%, right? So how is it then that an increase in kVp gives us twice the exposure? Well, where are you looking at the kVp, right? So when we say a 70% increase in output, where are we talking about? From the tube. From the tube itself, so that is what we refer to as primary beam. So what you have is primary beam, secondary beam, or sometimes secondary beam is referred to as the remnant beam. It's what's left over after you get differential absorption inside of the patient. So that 70% increase from the tube, because we get more penetration through the patient, equates to a doubling at the image receptor. So does a 15% increase in kVp equal a 100% change, a 15% increase equal a 100% increase, or a factor of 2, a doubling of the mass? Yes and no. At the image receptor, it absolutely does, but output from the X-ray tube, no. So which one of those are you most likely to get on as a question on a test? It's going to be at the image receptor, okay? So in that context, yeah, 15% increase in kVp doubles your mass. Doesn't double your mass, but it gives you the same effect at the image receptor as doubling the mass. So doubling the mass means doubling that tube output, right, tube current, which gives you a doubling of the number of X-ray photons that you create, and therefore emit. But the 15% increase in kVp does not double the tube output. It will change, however, how much penetration you have. An increase in kVp is going to give you more penetration. So that 70% increase in numbers, more of those numbers are going to penetrate. The effect in the remnant beam, secondary beam, post-patient X-ray beam, and at the image receptor will be the same as doubling the mass. So the context is that a 15% increase in kVp doubles our exposure, all right? Very important distinction. It does not double the exposure from the X-ray tube. It doubles the image receptor exposure. It doesn't double the patient exposure. So if you increase your mass by a factor of 2, then you increase, the only thing that changes in that brim spectrum is the height of the spectrum. That height representing only numbers, doesn't change penetration, doesn't change average, doesn't change anything else, it just changes the numbers, then it's going to change the numbers at all energy levels. So if you double your mass, you double the patient dose, right? That's not going to happen with kVp, and we'll take a look at that here in a minute. So claim number 4, kVp can be used to change image receptor exposure. True. Yes, it can, because if you increase your kVp by 15%, and again, that's the only thing that you do, then what happens to the image receptor exposure? It doubles, right. So let's say you make an exposure. You make an exposure, and you look at your index number, and your index number, depending on the manufacturer, they really should, make this thing universal. But depending on the manufacturer, your index number comes out either too high or too low, indicating that you have underexposed patient, okay? Realistically, looking at the image, you probably aren't going to be able to see much of a difference. It's going to look like a diagnostic image, but you've got to repeat it anyway, because maybe you clip the apices on a chest X-ray. So you're going to repeat it anyway, so why not change your technique? Why not fix your technique, right? But you don't want to double the patient dose, okay? So here's the thing. And this is kind of a rabbit trail, but it's worth going down right now. So if you have to repeat an exam for either over or under exposure, your starting point for changing your technique is a factor of 2. Okay, so if you overexpose a patient, then you need to cut your mass in half, right? You underexpose a patient, you need to increase by a factor of 2, all right? So you're going to confuse two rules there. The 30% rule is the minimum that there might start to be some sort of recognition in the system that there was some sort of change. But if it's worth repeating, it's worth changing by a factor of 2, okay? Okay, you're going to get questions that ask you, okay, you need to repeat an exam because of technique. So you need to repeat an exam because of technique, specifically because your index number was too high or too low. Your starting point is going to be a factor of 2, always 2. 30% is just to see any kind of noticeable difference. You really won't, but you know, that's the test answer is noticeable difference, 30%. Worth repeating, your minimum change is a factor of 2. Okay? Well, how much of a change in kVp gives you the same as a factor of 2 in mass? 15%, right. So let's say you shot this chest x-ray, and let's say as a young patient, right, a young woman, she's got developing breasts, you have to repeat it, you underexpose the patient, okay? So you underexpose the patient, plus you clip the apices, so you need to repeat it. If you double your mass, how much breast dose increase is that for the patient? If you double your mass, it's a factor of 2. If you increase your kVp, is it a factor of 2? No, because you're going to have more penetration, less photoelectrics in the patient, but how much of a change at the image receptor are you going to see? A factor of 2. So a few takeaways from that. High kVp low mass, a better technique for patient dose, or low kVp high mass? High kVp low mass, right. So so can you use, in that case, kVp to affect a change at the image receptor? You got a young patient, female, developing breasts, you've got to repeat because you clipped anatomy, and you were underexposed. Which technical factor do you change in order to make the change at the image receptor? kVp, right. So I'm going to throw some personal opinions on that later on, but for right now, most of the time that you're going to make a change to the image receptor is going to be mass, but there are times that you would use kVp. That would be an example. To limit the increased dose of the patient, you would increase kVp. So yes, you could, in that case, use a 15% increase in kVp to affect a doubling of the image receptor exposure without doubling the patient's dose. Okay? So can kVp be used to change image receptor exposure? Yes, absolutely can. So claim 5. So we already talked about increases in kVp can increase patient dose, does increase patient dose, can increase in kVp decrease patient dose. Yes, in context. All right, so we have 2 things that you're going to have a tendency to kind of conflate. All right, so you've got a 15% change in kVp. 15% change in kVp equals how much of a change at the image receptor? If kVp is the only thing that you change. A factor of 2, right. So the image receptor exposure changes by a factor of 2. So then let's say we go back to that same patient that we were talking about before. All right, so your index number showed that you made perfect exposure, but you clipped the apices. Still got to repeat it, right? You still don't want to increase the patient's dose. You still want to maintain the same image receptor exposure. What can you do? Because if you go back in and shoot her with the exact same technique, you're going to exactly double the dose. What can you do to not have as high a dose to that patient?
Lower mass about kVp.
Decrease mass, increase kVp. Increase kVp by 15%, cut your mass in half, right? So, if increase in kVp increases tube output by 70%, but doubles image receptor exposure, what that means is more of that 70%, more of that increase is going through the patient, striking the image receptor, not being absorbed into the patient. What type of interactions in the patient drive patient dose? Number 1 is total absorption, which is photoelectric, right? So Compton,
That's partial absorption, right? Even if they penetrate through, they still lost some energy in the patient, right? So it's partial absorption. So if the more of the photons that we can get to come out of the patient, the lower the patient dose. So increase kVp, reduce mass, reduce the patient dose. So both of those things can be true. kVp, so read your questions carefully. If your question just says you increase kVp, what happens to patient dose? It increases. If you increase your kVp by 15%, how much of a change at the image receptor? Factor of 2. What happened to the patient dose? It increased. So if you use, though, what we refer to as a 15% rule, and that is a change in kVp by 15% and an opposite change in mass by a factor of 2, then what would happen to the patient dose? It would decrease, right? Okay? So, how do we get to that? Well, a couple of different ways. One is if you're setting a technique, if you're doing portables, you just directly set it, right? Increase your kVp by 15%. Do the math in your head, you get close and it's going to be fine. Right? And if you have a hard time with percentages, 15%, sometimes it's easier to just take 10%, right? So what is 10% of 70? 7, right? So what's half of that? 3.5, right? 3.5 plus 7 gives you 15%, right? So that puts you at, 77.5 kVp. Are you ever going to be able to get to 77.5 kVp? Do you think that half kVp means anything in the world? No, it does not. All right, so 77, 78, either one, your image is going to be identical. All right, so use the 15% rule. When do we use the 15% rule? When we want to maintain image receptor exposure and reduce patient exposure, right? Increase kVp by 15%, reduce mass by a factor of 2. There used to be a world in which we lived where you might want to bring out more contrast, and you would do the exact opposite of that. Your contrast now is not really controlled by your kVp. We're going to get into that. It's not really controlled by the kVp anymore, so there's really not a true example of where you would want to reduce kVp and increase mass in order to increase your contrast. Your contrast is going to be controlled by your computer algorithm. It's what we refer to as the lookup table. It is your computer algorithm that's stored inside of the computer. It's what controls your contrast. kVp doesn't really control, isn't recognized as controlling the contrast anymore. How many of y'all on the Facebook pages for radiology? A few? Okay, so how many times have you seen people post questions about kVp and contrast? Any? I see it all the time. I see it all the time. If you look in the ARRT content specifications, there's that table that I showed y'all. You remember seeing that little table? If you look at kVp and you look at contrast, there is nothing there, okay? So when you get to the registry, a penguin you don't need to have in your head is kVp controlling contrast. It does not control contrast anymore, okay? It's your computer algorithm. So just flush that. Every time you see one of those questions, instead of trying to memorize, kVp and contrast, forget about it. Just pass it by, okay? It doesn't matter. You're not gonna see it on a test. Used to have context, it doesn't anymore. So, again, math oversimplified. If you have 80 kVp at 32 mass, it produces 100 units of radiation exposure to the patient. Increasing kVp by 15% to 92 would increase output by only 70%, not double. If that translated directly to patient dose, the new dose would be 170 units, but it wouldn't, because you'd have more penetration. But just to keep it simple, if then we reduce the mass by a factor of 2, the image receptor exposure would still be a factor of 2, but the patient dose would decrease. It would be now at 85 units instead of 100. So with the increase in kVp and a reduction of mass, patient dose goes down. That is the 15% rule. Okay, you need to change your kVp by 15%. That's usually going to be, to change image receptor exposure. 15% rule is to maintain image receptor exposure. 15% rule, if you see that in the question, not in the answers, in the question, 15% rule, always be thinking changing kVp by 15%, opposite direction with mass by a factor of 2, always. Okay? All right, so again, a little bit of beating a dead horse, but just for to demonstrate. So we're back to our original techniques that we were looking at before. So 72 kVp at 2 mass, 82 kVp at 2 mass. We got 90 photons originally. We got 153 photons over here. And what we get then is an increase in absorption, an increase in scatter radiation. We get an increase in transmission. Notice the transmission is double the transmission, so we get double the image receptor exposure. What you did not see is a doubling of the absorption, nor a doubling of the scatter radiation. Okay, so what do we say happens to scatter radiation when we increase kVp? Scatter increases, right. Okay, so let's go to the next one. We applied the 15% rule. We've got 82 kVp at 1 mass, so we've got the same image receptor exposure. So then we've got absorption, decreased, scatter, decreased. All right? And then we've got the same image receptor exposure. Okay. So what happens as kVp increases is if the only thing that we increase is kVp, then scatter is going to increase. Okay? But there's two things at play here. It's the numbers versus the percentage. So what happens as we increase our kVp is the numbers increase. All right? That's absolutely true. The numbers increase. You increase your kVp and that's the only thing you do, the numbers are going to go up. But the percentage, the amount of increase, the percentage of increase is not going to double, or is not going to increase as dramatically. All right, so looking back at these two, what happened with our kVp? Our kVp went up. So what we had over here was 33%, 33%, 33%, right? So if this was 33%, what would that number be? We increased our, well, I've got it worked out elsewhere, but it would be, I don't have a calculator up here. So I'll have it right here. We'll look at it here in a minute, but our percentage of photons absorbed actually decreased. Okay, so we'll take a look at that here. All right, so this is a 15% rule in practice, and this is historical context. CR is probably still going to be on your registry, so this is something that you probably ought to hang on to. This is not, I don't think I have this on test. We'll get into that when we get into CR and DR. All right, so when we use screen film radiography, what we had were image receptors that were 400 speed, and that's just a number assigned essentially that tells you how much radiation you need, and the higher the speed, the less radiation you need. Okay? So 400 speed is pretty fast. If you notice, 400 speed is here, and it's down here as well, even though those are O's instead of zeros. Because why? I don't know. 400 speed, they're the same speed, but when we went to the computed radiography, look what happens. 200 speed is going to be slower than 400 speed, which means that we needed to increase our technique. Okay, so here's the thing. back when we used screens and films, the thing that we had to use to control contrast, and that's why this is still hanging on for a lot of these old timers, is we use kVp. kVp control was what we used to control contrast. We had to use, adequate kVp to get penetration through the patient, but we didn't want it any higher than that because we would sacrifice contrast. Okay, differential absorption would go down, penetrate more stuff, we'd have more scatter towards the image receptor, it'd screw up our contrast. Didn't want to change our kVp. But now that we've gone to computed radiography, which has a lot of the same characteristics as digital as far as computer processing goes, what controls our contrast? The algorithm, computer algorithm, the lookup table. Okay, so file that away. We're going to get to it. Lookup table. So you got two computer algorithms, kind of playing side by side here. You make an exposure, and you get a range of densities on your image. Okay, but inside of the computer is another computer algorithm that has the ideal look for that exam type. So let's say you shot a hand, or anything, it doesn't really matter. And if you could get into the computer algorithms, what you'll see is they're kind of a table, and they've got all these lines that go up and down, and that determines contrast and density. Okay, so let's say you shoot an exam and you make a computer algorithm, and that computer algorithm you use too high kVp, let's say, and your computer algorithm's all stretched out like that. All right, so your lines are just all over the place. The ideal computer algorithm is like that. So what happens in the process of processing your image, and it's what we refer to as automatic rescaling, is that it takes your banged up computer algorithm and it makes it try to look like this one. Okay, so what it does is it just kind of dials everything in so that magically your your hand that you shot with 80 kVp now looks identical to a hand that was shot with 60. Okay, so if that was what controlled your contrast and density and not kVp, then when we went from a 400 speed, very fast system that required little radiation to a slower speed system, well, how much radiation will we need here? I mean, the numbers are exactly, that's exactly twice as much of that. So how much radiation would you think that we would need here at the image receptor to maintain that image receptor exposure? Factor 2. So how do you get to a factor 2? You got two different ways. One is the traditional way, which is increase mass. But what's that going to do to the patient exposure? It's going to double it. It's going to double it. So what's the other way? Increase our kVp by 15%. Is that going to increase patient exposure? Yes. Is it going to double it? No, no. So if you increase your kVp by 15% here, is that going to mess up your contrast? No, it's really not. So when we went from film screen radiography to computed radiography, did we see an increase in patient dose for every exam that was shot? The answer is yes, we did. The selling point for CR was, though, that we could potentially lower the overall dose to the population by limiting the number of repeats that we shot for bad technique. All right, and we'll get more into that later on. But when we went to digital radiography, look what happened. Our image receptor speeds went back up to 400. So now we're at 400. kVp still doesn't control our contrast. We want the same image receptor exposure that we had here. What are we going to do? We've got exactly twice as much radiation as we need. What are we going to do? Go back down on our kVp? mass. We just reduced the mass. So from here to here, what happened to patient dose? It went up. From here to here, what happened to patient dose? Cut in half. From here to here, it also decreased, but not by half. So here's my opinion on, kVp levels and the things that we do, to adjust image receptor exposure. Why not use more kVp? Why are we still using an increase in mass to affect a image receptor exposure, a change in image receptor exposure? If we need a decrease, yeah, I can see decrease in mass, but if we need an increase, why are we increasing mass? Why are we not increasing kVp? That's a legitimate question. I'm asking you because I have no freaking idea. I really don't. I have no idea why we're not increasing kVp instead of mass. I think it's just because mass is what we've always done. I think that eventually, in your career, and I've been saying this for about 5 years, and it hadn't happened yet, but I think in your career, the industry is going to wake up and they're going to say, yeah, we don't need to be increasing mass, that's just driving patient dose. And they're going to go to kVp. And it's going to be pretty abrupt, right? So you'll probably have to change to that, and you'll have to kind of pivot on a dime and stop using the increase in mass, but use the increase in kVp for inadequate patient exposure. I really think that on all our exams right now, we could just increase kVp by another 10 kVp, which would drive our mass even lower. I don't think we'd see any difference on the image receptor. So anyway, that's 15% rule in practice. So we got an increase in kVp, a decrease in mass. Our patient dose decreased significantly between screen film radiography and digital radiography because we can use higher kVp. Does not affect our contrast, and we get the same image receptor exposure. So when do we use it? When we want to affect a change in patient exposure without affecting a change at the image receptor. Usually it's going to be an increase in kVp with a reduction of mass, and it's usually going to be in specific populations. You have a pregnant patient. Sometimes we got to do it, right? Sometimes we have to take an x-ray on a pregnant patient. Do you want the patient to absorb a whole lot of radiation? No, I mean, in rare cases, we even have to do a KUB. A pregnant patient or AP of the L spine, patient's in a wreck. The baby is secondary in the wreck, right? We got to make sure mom's okay before we can worry about the baby. You might have to shoot, APL spine or a KUB on a patient who's been in a car wreck and she's pregnant, big, obvious pregnant. Might have to do it. So how could you limit the fetal dose? Increase kVp. Use 15% rule. Use 15% rule twice, right? Increase by 15%, cut it in half. Increase by 15%, cut it in half again. Lower the dose to the patient. Okay. So usually that's going to be the case. Are there potential complications? Yeah, I put contrast in here with a question mark because, again, you're going to see that, or you might even, hear one of the technologists that you're working with mention, well, we can't increase kVp anymore because it's going to affect contrast. Just know that it's not, and when you have the authority to change kVp instead of mass, change kVp. But there is one potential problem, and I really think this is even going the way of the dodo bird, and that is the higher the kVp that you use, the lower the mass you use. What are the two components of mass? Milliamperage and time, right? So you got two things there. First off, the definition of quantum model is inadequate exposure at the image receptor, right? So if kVp increases enough and you reduce mass enough, then you could introduce quantum model. Quantum model is kind of like a bad signal on your radio, as if anybody listens to radio anymore. You're driving out of the area and you start to lose reception, right? Or bad reception on your TV. You know, if you've got dish or something, sometimes if it's really stormy, sometimes you lose some reception and your picture gets all wonky. That's kind of our version of that. Quantum model, quantum, quantity. Model is kind of speckly appearance. So quantum model means a speckly appearance on the image because you don't have enough mass. So if you increase your kVp enough, you can get a modelly appearance, a speckly looking appearance. That's what that is. Okay, so the potential hazard, I say potential, is that if your kVp gets high enough, your mass gets low enough, then you could introduce quantum model. If you factor in inherent inconsistencies of low mass values in your timer circuit, it can even make it worse. Now, again, I put that under potential for this reason. Our image receptors are so sensitive now, I don't even know that quantum model is a thing anymore. In your sophomore imaging class, you're going to be doing experiments. And I've had students in the last 2 or 3 years try their dead level best to demonstrate quantum model on a digital image receptor. Could not do it. Highest kVp they could get to, lowest mass value, just lowest mass. About the only way that you're going to get to quantum model is the most minimalist kVp with as low a mass as you can get. You're just not getting any image receptor at that point, exposure at that point. So within a reasonable range, you may never see quantum model except for in textbook. So there are potential complications, probably not. All right, so claim 6, as kVp increases, all interactions decrease. And that is, again, true within context. So when you increase your kVp and change nothing else, then you, again, increase output from the X-ray tube. You increase the number of photons at all levels, but you increase the average and you increase that peak energy. Well, what's likely to happen with that peak energy? Absorption or transmission? Transmission, right. So already just including the peak energies, then that's going to skew the imaging characteristics and the types of interactions inside of the patient, right? Even if you didn't increase the height, if you just increase those peak energies, then you're going to get more penetration through the patient, which means if you get more penetration, the relative number of absorption and scattered photons decreases. Does that make sense? So all of the X-rays you create before the interaction, they're still there, right? You still create those same ones, but what you get more of are the high energy and also the higher average. So the added higher energy is more likely to penetrate. So this is, again, the numbers versus the percentage. Okay, so you increase your kVp all by itself, the numbers increase, right? The number of scattered photons increase, the number of photons photoelectrically absorbed increase because the entire Barem spectrum goes up, right? But the percentage actually goes down. I think Amy was going to touch on that. I don't know. Did she touch on that this morning? We were talking about it recently. Or maybe that was with the sophomore students. Okay, so interactions in tissue. So we're going to introduce, another thing here. So interactions in tissue with changing kVp. What you're going to see is as we increase our kVp, our photoelectric absorption, that's kind of fuzzy, I get it, in all tissue types decreases, right? The thing that remains relatively constant, but yet still dips a little bit, is Compton. So Compton is relatively unaffected by either tissue type or voltage. So what we're really talking about in increase in scatter radiation is increase in the scatter relative to especially absorption. Okay? So that's what we refer to as the Compton to PE ratio. So at these low kVps, we've got 20, 40, 60, 80, 120. At the low kVp, at 20 kVp, what is our photoelectric absorption? It's, I mean, we don't even get there until we hit about 60 kVp. So at 60 kVp, what's our photoelectric absorption? High or low?
High.
Very high, right. At 120, almost nothing. What happened with Compton?
Slowly decrease.
Slowly decreased, but not a whole lot. So where we have percentage-wise, our photoelectric is very, very high, right? At low kVp, really low at high kVp, right? And then our Compton remains relatively the same all the way across the board. It changes a little bit, but not significantly. So does Compton decrease?
Yeah.
Yes. Okay. So if Compton decreases, okay. So do the photoelectrics decrease with the increase in kVp? Yeah. So what's the only other thing that we've got there? We've got really 4 types of interactions. We focus on 3. One is not really an interaction, right? It's penetration without interaction. So naturally, if our kVp increases, our Comptons decrease a little bit, and our photoelectrics decrease a lot, what happens to transmission? It goes through the roof, right? So when we talk about scatter increasing, it's the scatter to the Compton to PE ratio. Okay. I think I just said that backwards. Or no, I didn't. No, I didn't. So penetration goes through the roof. So our photoelectric decreases, right? And our Compton increases. So did the numbers increase in this diagram? Numbers in both cases decreased. Right, but the percentage of the Compton at this crossover point, the percentage of the Compton is much greater than the photoelectric. Right? So that's the nuance. That's the you know, the context is Compton to PE ratio. Right? As kVp goes up, we get more scatter radiation proportional to the photoelectrics that we get. All right, so as kVp increases, all interactions decrease. If you increase your kVp by 15%, change nothing else, you increase output from the X-ray tube. You increase the number of photons at all levels, you will increase the average as well. All the X-rays you create before interact exactly as they would have before. The higher photons that are created with the increased kVp are more likely to penetrate without any kind of interaction. The added higher energy photons are more likely to penetrate without any interaction. So, you know, again, you get more penetration, fewer photoelectrics, fewer Compton, but more Compton relative to the photoelectrics. So yes, all interaction types decrease. Photoelectrics decrease at a more rapid rate than Compton. Compton remains fairly unaffected by kVp, right? Or even tissue type. Low kVp will create higher rates of, well, let's park on that for a second. Or tissue type. All right, so so what we have in these two lines is the difference in Compton in soft tissue versus bone. Okay? So, did it decrease in bone? Yeah. Is it significant? Not really. But what can you tell me about bone versus soft tissue? It's denser, it's more compact. So you got atoms that are a whole lot closer together, right? So if you create scatter radiation in bone, let's say it hits the first element, whatever it is, be it calcium or whatever, in the bone, and it scatters, and then it hits the next one, what happened in the first one? It's partial absorption, so it lost some energy, right? So it hits the second one. How big are atoms? Really little, right? So it hits the second one. And, the cortex of the bone is maybe quarter, half-inch thick. Hits the second one, and then the third one, and the fourth one. How likely is it to penetrate through the bone? Not very, right? So a scatter event, for it to hit the image receptor, has to penetrate through the patient. So what we're just talking about here is single scatter events. So is it more likely to scatter in bone or soft tissue? Well, soft tissue, but not by a lot. Is it more likely to scatter than penetrate through soft tissue or bone? Soft tissue, right? So your scatter radiation will go on sometimes and penetrate, or it will eventually bounce around and photoelectrically absorb. That last interaction, photoelectric absorption, doesn't include all the scatter events that happened before. Does that kind of make sense? You all got that? Okay, so low kVp will create higher rates of photoelectric, high kVp, low rates of photoelectric. Low kVp will cause low energy Comptons to become photoelectrics, whereas high kVp will cause more penetration of all types, including those Comptons. Using the 15% rule, you can see how an increase in kVp can reduce interaction and patient exposure. So, summary. If we increase kVp alone, the likelihood of and percentages of all interactions decrease. The overall numbers of interactions increase. If we go back to slide 29, we can kind of look at those numbers and the percentages here. So again, with an increase in kVp from 72 to 82, we got a decrease in photoelectric absorption, we got a decrease in scatter radiation, and we got an increase in penetration. Right? So these numbers over here we're going to take a look at are, low, the difference between these two, but they do change a little bit. So, and we just talked about that. Increase in kVp, does it increase scatter? Well, that's true in context. PE ratio, just overall numbers. If we increase our kVp, all interactions decrease, but relative to photoelectric, we get more Compton scatter radiation. So, and those Compton photons that we create are more likely to penetrate. So remember that penetration is not just penetration without interaction, it's penetration without interaction plus penetrating Comptons. So as we increase kVp, the Comptons that are emitted from the patient increase as well. So at the image receptor, we do get an increase in scatter radiation. All right, that's kind of what all that says, but just to sum it up, the Compton to PE ratio, a ratio is like 1-to-1, but at 72 kVp in our example on slide 29 was 33 to 33, at 82, it was 30.7 to 30. So, you know, it had changed. It's not equal. We got a decrease in photoelectrics at a greater rate than we got a decrease in Compton's. Okay, so kVp and scatter radiation. We're probably not going to get off of kVp and scatter radiation today. So on Bushong's 122 and 157, with an increase in kVp, more X-rays are emitted and they have higher energy and greater penetrability. Unfortunately, because they have higher energy, they also interact more by Compton effect and produce more scatter radiation. Okay, so that sounds like a contradiction of what we just said, but then on page 155, if you go back to 155, it says the probability of an X-ray of a given X-ray, I think I wrote that down wrong, that a given X-ray will undergo Compton scattering as a complex function of the energy of the X-ray. In general, the probability of Compton scattering decreases as X-ray energy increases. And to finish that off, but it decreases at a slower rate than what photoelectric does. Again, the Compton to PE ratio. Comptons, relatively speaking, go up, photoelectrics go down. Using higher kVp reduces total number of interactions, increases the amount of transmitted X-rays. In these interactions, Compton scatter increases, photoelectric decreases, and we get more scatter that exits the patient. At higher kVp, more X-rays are transmitted with fewer interactions. However, a greater proportion of the interactions are from Compton scattering than from PE absorption. That's out of Fauber. And then as X-ray energy increases, the absolute number of Compton interactions decrease, but the number of photoelectric decrease much more rapidly. Therefore, the relative, my word there, number of, or maybe better stated, percentage of X-rays that undergo Compton increases relative to photoelectric. So X-rays in diagnostic range also undergo ionizing interactions with intershell electrons. The X-ray is not scattered, but is totally absorbed. So that's your photoelectric effect. The probability that a given X-ray will undergo photoelectric interaction is a function of both the X-ray energy and the atomic number with which it interacts. So again, bone versus soft tissue. They're going to scatter in both of those, but they'll more likely absorb in the bone. A photoelectric interaction cannot occur unless the energy is equal to or greater than the electron binding energy, which always kind of seems a little contradictory to me. That seems to suggest the likelihood of photoelectric interaction increases with increased kVp. But no, if you go to the next paragraph in the penguin, the second penguin on the page, it says probability of photoelectric interaction is inversely proportional, and this is huge, to the third power of the X-ray energy. So what does that mean? As kVp goes up, the likelihood of photoelectric absorption goes down, and it's exponential, right? So it goes down by the third power of the X-ray energy. And the second penguin says probability of photoelectric absorption is directly proportional to the third power of the atomic number of the absorbing material. So now, applying all of that, photoelectric interaction can be single event, right? Probably not, but could be single event. Single absorption, one photon hits one atom, completely absorbs. Probably not going to happen. Probably going to bounce around and then absorb. All right. So why does bone show up so good and soft tissue not so good? Probability of photoelectric interaction is directly proportional to the third power of the atomic number of the absorbing material. So exponentially more absorption in bone than in soft tissue, right? But if we increase kVp, again, we can kind of overcome that. We, the increase in kVp, we get a
inverse relationship. The likelihood of photoelectric absorption is inversely proportional to the power of the X-ray energy. So as kVp goes up, photoelectrics decrease. As atomic number goes up, photoelectrics increase. X-rays can undergo interactions with outer shell electrons and not only scatter the X-ray, but it also reduces the energy and ionizes the atom. If you've read through the chapter, there's a reference to a movie that's called Straight Outta Compton. Yeah, Bushong's hilarious. It just doesn't come through sometimes in the written word, but that's what he's referencing there. So no, it has no relationship to the movie. And the movie's probably 40 years old by now, so you may have never even heard of it, you know. That's what happens when you get old, you tell the same jokes. What's that?
They redid the movie.
Did they really?
I think so.
I didn't know that. Okay, so maybe it's, yeah, maybe you have heard of it. So the X-ray continues with less energy, that's a scattered photon, equivalent to the difference between the energy of the incident X-ray and the ejected electron. So every interaction, it decreases energy. If it decreases enough energy, it becomes a photoelectric absorption inside of the patient. I think we're out of time, and we're not out of lecture. Let's see how. Yeah, we're, okay. So y'all want to pull up there?
Yeah.
Yeah.